Hello,
Hello, Marianne.
can you now hear me?
Yes, I hear you.
So I just want to make sure that like others also on that platform can hear me, but I'm not sure if they can. That's the issue right now because I don't have any other audio from, the event here.
Okay.
Perfect. All right. They say like we can hear you. All right, that's great.
I don't see any camera from the other speakers. Is it
Perfect.
everybody with the camera
Yes.
turned off? Oh,
All right.
yes, now.
Perfect. All right. I think like the technical issue is over now. Hello, everyone. Um, Good morning and a very late good afternoon from San Francisco here. It's around midnight
Wow.
and yeah, it's like 12, like some 5 minutes past 12 here. So I am joining you from a very quiet Bay Area right now. I am Mariam Hosseini. I am an assistant professor at the University of California, Berkeley. And my research is at the intersection of computer vision, urban planning, and accessibility for specifically for people with mobility and vision impairment. And I am also like an open source developer for the past 5, 6 years and even more. And I create tools and techniques to tackle the data scarcity and also the problems that we have with the design of the urban public spaces, specifically for them to be more inclusive and to have more inclusive cities. So I'm very pleased to moderate today's session on the emerging applications of AI in metropolitan planning and public service. We have an excellent group of speakers today whose work has spanned research institute and public agencies and also global networks focused on the challenging issues of the megacities today. So let me very briefly introduce our speakers. We have Dr. Jonyang Choi, who is the director of the Center for External Collaborative at the Seoul Institute and also leads the Megacity Think Tank Alliance Secretariat. His work focuses on urban analytics, metropolitan governance, and AI-supported planning systems. We have Mr. Ramon Pruneda Flip, who is the Chief Technology Officer at the AMB Informació i Serveis SA, the public company of the Barcelona metropolitan area that develops and operates the mobility applications and also information services for the millions of the daily users. And apologies if I'm not pronouncing the names correctly.
You did very well, thank you.
Thank you. We have also Dr. Kimon Jang, who is a postdoc fellow at the MIT Sensible City Lab, and he will also be soon to be an assistant professor at the HKUST. And his research focuses on generative AI and explanatory computation methods for complex metropolitan systems. And last but not least, we have Dr. Alec Heubrecht, the director of the International Affairs at the Institute of Paris region, and he serves as the chair of the MTPA GN. He has an extensive experience in international metropolitan cooperation and long-term regional planning. So our agenda today reflects the breadth of Meta's work and also the shared interest in understanding how AI can support more adaptive and also equitable and sustainable metropolitan systems. We will begin right now with an introduction of the meta, followed by three focus presentations. So after our second talk, we will take questions from the audience, and then we'll go back to our third talk. And also, we will close with a very brief wrap up. So, with that, I will invite Dr. Choi to begin with an overview of the meta. The floor is yours.
Thank you. Can you see my screen? It's good?
Yes,
Yeah.
but we are
Yeah.
seeing
Yeah.
you,
Yeah.
we are.
Yeah. Yeah. I will briefly introduce Meta and then right after the introduction, I will follow my presentation. So
I
the
think we have the presenter's note here.
We are
Maybe
so
you
seeing
want to share the other screen.
the
Perfect. Thank
presentation
you.
view. Yes,
Yes.
yeah. Yeah. My name is Junyoung Choi. I'm currently working at the Seoul Institute as a director of Center for Collaborative Research and also the director of the Meta Secretariat. The Meta is the Megacity Think Tank Alliance. Meta is an international alliance of think tanks. We focus specifically on addressing the unique challenges and opportunities inherent in megacities worldwide. Our primary goal is to bring together leading experts and institutions to share policy development, strategic initiatives, and research. Meta was founded on July 11th, 2014. Our initial founding members included the Seoul Institute, the Beijing Municipal Institute of City Planning and Design, BICP, the Singapore Center for Livable Cities, CLC, the Shanghai Urban Planning and Design Research Institute, and Ho Chi Minh City Institute for Development Studies. Furthermore, three international organizations, CityNet, Metropolis, and ICLEI, supported and actively participated in our founding. The purpose of Meta is to create a collaborative international network that facilitates the exchange of information on urban challenges and solutions among member think tanks. By coordinating problem-solving efforts and encouraging partnerships, Meta aims to support in fostering bilateral and multilateral cooperation to address urban issues effectively. Meta operates with a structured approach to ensure active engagement among members. English is the official language, and Seoul Institute serves as the secretariat. There are several types of meetings: Meta Forum, General Assembly, Academic Forum, and working level meetings. Meta is currently include 14 member institutions from Asia, Europe, and Middle East, comprising urban and government-affiliated think tanks, as well as two international organizations, CityNet and ICLEI. Uh, Together, these institutions collaborate on urban policy, planning, and innovations to address shared megacity challenges and promote sustainable development. Since 2014, Meta has held 9 forums across Asia discussing key urban issues like public space, mobility, and sustainability. The most recent, the ninth forum in 2025, was held in Seoul and gathered representatives from 19 institutions across 9 cities, including observers, highlighting Meta's growing global collaboration. Meta's activities are guided by its articles of association covering areas such as membership, governance, and responsibility. For Meta's operation in next year, 2026, three key joint research themes were proposed. First, AI megacity planning, proposed by Seoul, was formally adopted at the Ninth General Assembly 2025. Second, Paris suggested a data-driven urban policy approach, especially for addressing challenges such as housing crisis during bilateral discussions. Third, Singapore proposed the theme of a health city, which was also shared during the General Assembly. In terms of next forum, we are pleased to announce that the Beijing Institute of City Planning and Design, BICP, has been accepted as the hosting institutions for the 10th Meta General Assembly and Forum in 2026. Yeah, that is a brief introduction of Meta. And now I want to present my presentation. It is a AI-supported system for daily life zone planning, focusing on how accessibility and mobility-based approaches can define more realistic urban living zones. Although I'm from the Seoul Institute, the algorithm was tested in Busan, southern port city of South Korea, to demonstrate its applicability at the national level. The Seoul Institute, established in 1992 and fully funded by the Seoul metropolitan government, operates with 6 research divisions, one AI lab, and one center. It is home to 300 researchers and staff with a 2024 budget of 37 billion US dollar. Our research, this research is driven by three key factors. First, there is a growing interest in the daily life zone (DLZ), often associated with the 15-minute sleep plan. Following COVID-19, the importance of DLG, which focuses on short distance travel, has been significantly highlighted. Second, we reflect on the limitation of administrative convenience. Currently, the setting of DLGs often centered on administrative district boundaries, which inherently limit the scope of actual residents' daily activities. Third, there is a clear need for a data-driven approach to reflect real-world activities. Our primary purpose is to prepare a data-driven foundation for setting up DLG that genuinely considers the living activities of actual residents. Ultimately, this study aims to derive data-driven living areas that accurately reflect residents' actual activities. We focus on two main approaches for defining daily life zones. First, we analyzed daily life zone (DLG) based on the accessibility of neighborhood living facilities. This includes key facilities like kindergartens, elementary schools, libraries, and parks. Second, we analyzed DLG-based mobile data reflecting actual population flows and mobility. Our study area, the Gangdong region in Busan City, offers an interesting context characterized by being surrounded by the Nakdong River and mountainous terrain, and featuring a mix of industrial and residential areas. This diverse geography is crucial for observing how DLG is formed. This model supports community planning through three core functions: DLG planning diagnosis, plan zoning, and facility location support. It evaluates accessibility to neighborhood services and public transport and helps determine optimal locations for single or more complex service deployment. This study focuses on daily life zone rezoning using both living facility accessibility and mobile data as key inputs. This study focuses on the Gangdong region of Busan City, covering about 15% of the city population. The area includes mixed industrial and residential zones and is part of Busan's 2040 urban master plan. We apply the data-driven approach to define daily life zones using two criteria: accessibility to neighborhood living facilities and mobile data patterns. We then compared the spatial accuracy of each method using the IOU index. This study uses three key data sets. First, population data in a 100 by 100 meter grid helps identify residential patterns. Second, neighborhood living facilities like schools, parks, and welfare centers were mapped across 12 facility types and 545 locations. Finally, mobile visual location data in 50 by 50 meter grids was used to analyze actual movement patterns. This mobile data was re-aggregated to match the population grid for consistency. Uh, Our study applied two key methods for data analysis. First is the community detection method using the Rubin algorithm. This algorithm automatically identifies groups of strongly connected nodes by maximizing the modularity of the network. which helps us detect spatial communities based on structural connection patterns. It is especially efficient for analyzing large-scale urban data. Second, we use the intersection of a union or IOU to evaluate spatial similarity between different daily life zones. The IOU value ranges from 0 to 1, with 1 indicating perfect spatial overlap. This metric helps us compare the accuracy and consistency of community boundaries generated from different data sets. Our analysis follows a three-step framework. In step one, we extract analysis specific grid cells based on three data types: population, neighborhood living facilities, and mobile data using a 100 by 100 meter spatial grid. In step two, we perform OD metric analysis using OD pairs located within a 5 kilo radius and calculate the 20-minute walking distances with OSRM, the Python library, to evaluate the spatial reachability. Finally, in step three, we calculate the spatial weights using both facility accessibility and mobile population data. These weights are often applied to identify daily life zones through community detection using the Rubin algorithm. We compare two DLG outputs, one based on accessibility and the other based on mobile movement pattern. This step outlines the data pre-processing process within our analysis framework. We use a 100 by 100 meter spatial grid as the analysis unit, overlapping three core data sets: population data, neighborhood living facilities, and mobile user movement data. Facility coordinates are matched to grid cells, and mobile data originally in 50-meter unit is aggregated to align with the 100-meter scale. We then select a grid based on the presence of population, facilities, or the mobile population data. This spatial structuring ensures a consistent and comparable data set for the further analysis in daily life zone modeling. In step two, we conduct OD matrix analysis to understand the spatial connectivity. We define OD pairs as grid cell centroid that are within a 5 kilometer radius and reachable within 20 minutes on foot. To do this, we pre-process the grid cells, set origins and destination, and use OSRM, open source routing machine, to compute walking travel times between cells. Finally, we extract OD pairs that meets the time and distance criteria, which become the basis for constructing the OD metrics used in community detection and accessibility analysis. In step 3-1, we calculate the weighting values to perform community detection using the Rubin algorithm. Two types of weights are applied. First is facility accessibility, measured using the 2SFCA method, two-step floating catchment area. This assesses the spatial balance between supply and demand by evaluating how much population each facility can serve and how accessible it is to different grid cells. The more facilities and the fewer competing users a grid cells has, the higher its accessibility score. Second is the mobile-based weight, which reflects the volume of population flow between grid cells using OD data from mobile telecom users. We extract the origin destination pairs recorded between 8 a.m. and 8 p.m. and calculate travel time within a 20-minute walking distance. These weights are normalized and then used to generate two versions of daily life zone. One based on accessibility and the other on mobile movement pattern. This slide explains the analysis framework used to derive daily life zone or DLG. The process consists of three main steps. First, we extract relevant spatial grid cells based on population, facility, or mobile data. Then we analyze OD pairs within a 5 kilometer radius or 20-minute walking distance. Step 3, we calculate weights using facility accessibility and mobile population counts and apply the Rubin community detection algorithm to identify DLGs. Two types of DLGs were created, one based on accessibility and one based on telecom mobile data. We adjusted the resolution to 1.1 to ensure both DLG types produced a similar number of communities. After running the algorithm 100 times to account for randomness, we selected the final result with the highest modularity, normalized mutual information (NMI), and consensus score. Lastly, small communities were merged to improve clarity and interpretability. In step 3-3, we explore three main approaches for solving spatial optimization problem. First, linear program offers mathematically rigorous solutions and is effective when the problem has clear linear structures. Tools like Groby, Cplex, and Pulp are commonly used for this method. Second, heuristic and mathematical approaches such as genetic algorithms, simulated annealing, and tab search don't guarantee optimality but are practical under time or resource constraints and are highly flexible for complex real-world problems. Third, deep learning and reinforcement learning approaches, including reinforce and tools like SpanNet and LecGeoNet, use neural networks to learn decision fallacies. These are particularly useful for large-scale problems with irregular spatial pattern. This slide compares Life Jones DLGs derived from three sources: the government's existing plan, accessibility-based analysis, and mobile data. We observe that DLGs based on real data often extend beyond administrative boundaries, better reflecting the actual activity ranges of residents. In fact, multiple DLGs can appear within a single administrative dome, which highlights low spatial alignment with government-defined zones. Geographic elements such as roads, rivers, and terrain, along with the travel time, also significantly influence DLG boundaries. This indicates the importance of using real-world mobility and service access data when redefining community zones for urban planning. This analysis shows that daily life zone or DLG often do not match administrative boundaries. Zones defined by accessibility or mobile data extend beyond the official borders, reflecting when people actually move and live. We also see that one administrative zone can include several DLGs, highlighting the need for more flexible planning. Geographic features are and working time, like rivers, roads, and terrain, play a major role in shaping these zones. This slide compares government-defined DLGs with those generated from data using IOU values to measure spatial similarity. In residential focused area, we observe high alignment between data-driven DLGs and official plan, which support their use in managing infrastructure. However, in industrial and mixed-use zones, the accessibility-based DLG shows low spatial alignment. Interestingly, the mobile-based DLG display higher similarity, especially in areas like the, the southern part where the IOU reaches 0.8. This suggests the mobile population patterns can better represent real activity zones in complex urban settings. This slide compares the government-defined living zones with the data-driven DLGs, while accessibility and mobility-based DLGs generally align where they often diverge from administrative zones. For example, in areas in the middle part, the government designated them as a separated zone, but data shows they function as a single continuous living area. This suggests that planning based solely on administrative boundaries may overlook how residents actually move and use urban facilities. Additionally, we observe a positive correlation between the residential land use ratio and the spatial overlap IOU, indicating that database DLG better reflect lived urban reality. In conclusion, daily life zones or DLG are dynamic spatial units shaped by real-world mobility patterns, not fixed administrative boundaries. Our analysis shows that data-driven DLGs often extend beyond the known boundaries or form multiple zones within a single zone, indicating the need for planning based on actual human activity data. In residential area, higher residential land use ratio correlated with stronger spatial congruence between different DLG types. This highlights the role of physical accessibility and facility placement in stabilizing DLG structures. Data-driven methods can support more adaptive DLG planning and help close the gap between administrative planning and real behavioral patterns, ultimately enhancing spatial equity and urban connectivity. For future work, we propose expanding the spatial and temporal scope and including external populations such as inbound commuters and visitors to validate the DLG model more comprehensively. Thank you.
Thank you very much for the presentation. And I just now want to ask and invite Ramon to present his research as our second talk of the session.
Thank you, Marianne. Let me to share my screen with you. Could you confirm that? Are you seeing my presentation?
Yeah.
Yes.
Is it the AI to improve public services?
Correct.
Perfect.
Yes. This is the cover. Perfect.
Yes.
So thanks, Marianne, for your kind introduction and for your perfect pronunciation. And thanks
Thank
to
you.
ITU and the rest of the co-organizers to invite at this interesting webinar. My name, as Marianne said, is Ramon Pruneda. I'm CTO at the Metropolitan Public Company, AMB Informació. AMB Informació works for the Barcelona Metropolitan Area Administration. This is an administration that manages services for the 36 municipalities, including Barcelona City. For instance, the mobility and public transport services. Here you see the main competencies like the entry public transport network management, taxi licenses, bike and scooter sharing services, park and ride, or the management of low emission zones. So let me show this table. AMB Informació, our company, develops technical solutions and digital tools for these services. And we are in charge of managing multiple sets of data and information related to this. As you can see here in the table with some data volumes managed by organization, like the administration of concession card for the senior citizens to access with benefits at the Barcelona public transport network, or where we are managing more than 400,000 users, or the public transport services covering more than 6,000 bus trips per year, or handling 5,000 service disruption every year. Or last, the registration for access and control to the low emission zones, where we are registering more than 2 million vehicle plates every week in our data lake. So we are, or we have the framework to manage and take out value from this data, of course. Now, let me introduce a specific project. It's called AIDA project. It's a solution that we implemented for the Barcelona Airport shuttle bus. AIDA is a project built around machine learning, what we often call traditional AI, and it's designed to train an algorithm capable of predicting passenger demand. Our goal was to provide bus operators with accurate data-driven insights so they can adapt services levels dynamically and improve both efficiency and passenger experience. We decided to start the project on this particular bus lane because it's not conventional urban route. Instead, it functions as a shuttle service connecting Barcelona Airport with the city center. which means that the demand patterns are highly variable. They depend on, for instance, flight schedules, seasonal peaks, tourist flows, and even exceptional events. All these factors make the line an ideal candidate for a predictive AI model. So as I said, the main objective of the project is to develop and train a machine learning model capable of forecasting demand. But by understanding and anticipating passenger volumes, we are able to optimize fleet allocation, reduce waiting times, and ultimately make the entry transportation system more resilient and efficient, of course. But beyond that, we also use this project as an opportunity to analyze the impact of external factors on demand. This includes variables such as weather conditions, flight schedules, seasonal tourist patterns, etc. By incorporating this external data source into the model, we can gain a much deeper understanding of the underlying dynamics that shape demand. So in our model, we integrated historical demand data using several key metrics like the trip validation, ticket sales, the number of bus trips operated, and any service disruption that occurred. In total, we built a data set containing 2 full years of this historical information. But as I said, we didn't stop there. We also incorporate these external variables by training the model on this combination of internal and external data sets. We were able to obtain a much accurate prediction, as I said. We test different machine learning algorithms, evaluating their performance using metrics like the R-squared, and eventually selected gradient boosting regressor as the most reliable model for this scenario. Now I don't want to spend too much time on the technical details or on this, for example, these heat maps graphics that you can see here. But the key message that I want to share is that we now have a tool capable of predicting demand of this service with about 85% accuracy 1 week in advance. So we have this possibility with this predictable tool to obtain this forecast demand with this 85% accuracy. This means that our public mobility technicians or also the bus operator now have a complementary data-driven insights to help them plan service more efficiently, improving the operational quality. So at this point, I would like to share the 3 main conclusions of this machine learning project. The first one is that there are significant differences between generative AI and traditional AI or machine learning. Of course, that generative AI helps us to automate tasks and improve productivity, but machine learning solutions create direct value for public and private organizations because they extract insights from their own internal data. The second conclusion, there is a clear need to truly believe in and commit to that a data-driven strategy. A data-driven strategy transforms an organization with the data, and the core decision-making is not easy. It requires addressing several key aspects, like security, data quality, and availability. Also, is very important, not only the quality of the data, if not also the availability, the access control at this data, anonymization, standardization, deploy technical platform and infrastructure, and maintain and analyze the economic viability of this implementation, the legal and ethical frameworks, acknowledge and training of your teams. So in short, solid data governance is essential to become a data-driven organization. And the last conclusion, the third one, is that implementing these machine learning solutions requires a significant investment, both in time and in specialized talent and resources. So these 3 points reflect the main learnings from our project and highlight what organizations must consider when adopting machine learning technologies. I always like to show this sentence because it's very clear that about the idea that I want to transmit. It's a sentence from Mr. Edwards Deming. This is an American consultant that works with Japanese government at the end of the Second World War, and that he said that in God we trust, all others must bring data. And let me add, all others must also be data-driven, as I said. Okay, now let me show you a high-level overview of our data platform from a technological perspective. The goal of this slide is to give you a sense of the complexity and the importance also of managing both data and metadata across different domains. What we use is a data mesh architecture. So you can see here in this scheme that our data mesh architecture, which you can think of as a hybrid between a traditional data warehouse and data lakes. This approach enables us to handle data ingestion, ETL processes, and exploitation of data through business intelligence tools and AI developments. To generate real value, it's essential to build architectures capable of integrating data from multiple domains in a unified and consistent way. This cross-domain integration is what allows us, for example, to understand what happens, for instance, when a park and ride services, what happens in a park and ride services when we implement a new low emission zone, or for instance, how does ridership increase when a bike sharing station is temporarily out of service. So at the end is understand in an integrated view these different domains. This capacity to connect and analyze data across domains is key to supporting better decisions and smarter mobility services. So now allow me to show you some examples of our business intelligence tool. And these tools is available because we implement this data government strategy and this technical platform that I show you. Here, for example, you can see the key indicators of the metropolitan bus services operated through different concessions with private operators. As you already know, with these business intelligence tools, we can integrate real-time data. We can select the temporal granularity that we want, if we want to see data from 1 day or 1 week, or we can inspect details by municipality or by bus line, and so on at the end. So keep in mind that our public managers, for instance, administer dynamic contracts, dynamic public contracts sold by public tender with the operators, with private operators, with an economic penalties and bonuses depending on the quality of the service that they provide. So our public technicians are managing these dynamic controls, monitoring these services, and make decisions through this business intelligence tool that you show here in these slides. Here you have more examples, and for instance, the request and operations for delivery freight, for loading and unloading of goods in the city. So we can see by municipality, we can see in a data, in a maps, etc. And now to finish, let me very briefly share with you some of the main projects that we have been developing with the generative AI, because I show a use case and example done by traditional AI, as I said, or by machine learning solution, but we're implementing also projects through generative AI. This is, for example, a chatbot built using OpenAI APIs. This is the typical RAG chatbot based in a RAG architecture based system that provides specialized information about the metropolitan services. One of the biggest efforts in this project was preparing the vector knowledge base. So the model now could answer citizens accurately within the specific domain that we needed and that we specialized the chatbot. Today, this service handles more than 3,000 questions every month, and we are seeing a satisfaction rate of over 92% based on the responses that it provides. No? And of course, following the requirements of the European Union AI Act, we assess the risk of the solution. We clearly inform users about the technology behind it and about the possible limitation in its answers or the possible mistakes. And we have also published an algorithm transparency sheet for this tool in our website. Now, this is another project. This project is about automating an administrative process using generative AI. So for each vehicles entering to Barcelona city must register to obtain permits to access at the low emission zones. And in this case, for the Spanish vehicles, we retrieve the data via the license plate from the general Spanish vehicle registration. So with the number of the plate in the Spanish vehicles, we can check, we can look for this information in the general Spanish vehicle registration. But this information is not shared between European Union countries. So with a number plate of friends or for instance from Italy that comes to Barcelona, we cannot know what is the mechanical or powertrain characteristics of this vehicle to process the permit to access at the low emission zones. So now the process, the French or Italian or Belgian driver who want to register in the low emission zone have to upload the vehicle technical sheets, and afterwards, administrative staff of our company had to manually check the technical sheet to determine whether the vehicle was electric, hybrid, or Euro 6 diesel, for instance. But this is the old process. Now we have implemented a model that, doing a little bit of joke, we call this model as the AI party because we put in the same tool a Google, Microsoft, and OpenAI to work together in this same process, where in an automated workflow, we use Google Vision to extract data in JSON or in text format from the photos or the PDF of the technical sheets that the users send us. We run the data through an anonymization process with Presidio Microsoft solution, and then we structure the response for the back office using OpenAI APIs. As a result, our public administrators not longer validate the technical sheets one by one. Instead, they supervise the results of this automated process, drastically improving process efficiency. And last to finish, as I'm a member of AI working group from the UITP, is the International Organization of Public Transport. I want to share with you this publication. We publish. This is a book of different use case based on AI in the public transport from different countries, and you have here the link to look for this publication. It's very interesting. Here you have some examples I will show you very quickly because it's not our example, it's done by other entities. Like for instance, in Singapore, you can see this digital sign language avatar for the deaf. So with generative AI, they are giving information with sign language avatars for the deaf users in the public transport network, or for the visually impaired users, using also a AI generative solution to learn about the bus stops. What is the information of the arrival time or the bus lanes, etc. They develop these projects, or for instance, a chatbot for the staff in the chamber done in Netherlands. So that's all. I think that I'm in time. Thanks for your attention, and I will answer your questions after the webinar.
Thank you very much for the amazing presentation. Very interesting, and I think maybe our audience also will have some questions to ask. So we want to have some minutes just dedicated to take the questions. If anyone has any type of questions they can use, there is this button on the platform. I think it's called video wall that you can use. Like there's a tab on the platform that you can use to post your questions there. Also, we have one question from one of the audience, Dr. Natalie Aris, who asked Dr. Choi if do you see any opportunities to collaborate with other initiatives and city networks, for instance, Milan Urban Food Policy Pact, which is a network of 330 cities working on food policy and developing sustainable food systems that are inclusive, resilient, safe, and diverse. So, Dr. Choi, is it something that you would or you want to consider?
Yeah, the originally this project is funded by the National R&D program, and where the priority is on the applying this approach to the local government of Korean city, local government of Korea. But the Seoul Institute as the secretary of METTA, Megacity Think Tank Alliance, and also the global collaboration in terms of global collaboration, we are open to the other cities to collaborate on these algorithms. Yeah.
Perfect. Thank you. So, do we have any other questions from the audience that we want to go to, or we should move to the next question, like to the next speaker? All right. So, if we don't have any questions, I think we can move to our next speaker. And let me see if there is any other questions here. No. So, Dr. Kimon Jang, I think the floor is yours, and we are waiting to hear about your research and talk.
Thank you. Let me share my screen.
Perfect. We can see your screen now.
Okay. Well, hello all. My name is Ki Moon Jang. You can call me Ki. Thank you for having me for this webinar series from AI for Good. Today, I will be talking about generative AI, not going too much deep into the technical details, but it'll be more of an like an exploration of how generative AI technology, pretty much in open source formats, can be used for various urban tasks, and what are the major implications when it is to be applied in metropolitan planning or city planning in general. So we all know about ChatGPT. It has been released pretty much about like 3 years ago, and it is dominating the world. And it's not only about ChatGPT, but since the release of GPT models, there has been a bunch of different kinds of generative AI or large language models, in a more technical term, that has been published in different kinds of their own, also being published in different kinds of private services that you can also subscribe yourself for various different kinds of use cases. And then it has been tested since then for its application in different domains. One of the most famous videos when the GPT-4 was released was when it was tested for tutoring services. So it can now have a multimodality capabilities, understanding the images like hand drawings, interpret the information out of that, and then also being able to interact with natural language promptings. There's also an online quiz solver, so now people are coding it, making a plugin that can be embedded in your web-based platforms so that it can search through the web automatically and get you the most relevant information of your interest. And it has been also tested for various kinds of professional exams, especially the well-known cases is that it has passed the bar exams to become an attorney, or also the medical school exams to become doctors. But as urban planner or urban designers, I was wondering what it would be like if it is applied to any kind of city planning tasks. So that is going to be the main question, the underlying question for using generative AI for urban practice. So I'll today briefly introduce about two previous projects that I've worked on, starting off with this one titled Multimodal Large Language Models as Built Environment Auditing Tools. So this will be a more of a practical exploration of how it can be used in a very specific task of built environment auditing. And the built environment includes the physical makeup of the cities, especially of the streets, which is one of the main focus when it comes to built environment auditing. And auditing can be done for very specific use cases, such as to assess the infrastructure elements, or maybe very strictly focusing on whether the streets are walkable, whether the streets are bikeable, how well is the food environment prepared for the city residents, and so on and so forth. So how it has been traditionally done is these field audits. So pretty much the city government people would go out in the streets with their checklists that looks like this. This is a built environment auditing report, particularly for bikeability. As you can see from the list, there's a bike rack accessibility, bike rack availability, and so on. But the problem here was that this people going out on the streets checking all these information are very labor intensive, sometimes time consuming and very costly, especially when you want to scale up at a very large scale. And it, especially for metropolitan cities, it becomes much more time consuming and costly. Uh, Probably virtual audits were one alternative to solve these issues. So they try to have these GoPro or maybe any sort of visual information that they can collect of the streets and take it back to the office and then look at the images or videos and then use that for the auditing processes. And then maybe even further than that would be how if you can either automate it with the pre-developed deep learning based computer vision methods. So this is one study that has tested the availability of image segmentation models in detecting specific objects or specific urban elements that maybe or that is commonly included in the street environment assessment tasks. So as you can see from here, it is assessing whether there's a tree, whether there's a street walk, and then there's a crossroad, and so on and so forth. However, this also has a remaining challenge in that it requires technical expertise. And of course, it requires a lot of access to computing resources. We're not going to make all the city governments be very well equipped with Python capabilities, learning about YOLO technologies, applying deep learning for these simple tasks. So, and then now this was done last year when the GPT 4.0 model was released. And looking at its, and given its multimodality capabilities, we are interested in if it can interpret images as much as possible as conventional deep learning technologies. And then if so, pretty much we assume that it can be used in a very applicable manner to conduct built environment auditing tasks in also very readily available. So if we find so, we believe that this such a user-friendly tool can be very much applicable regardless of the technical competence of users and thus reducing the time and cost involved in such auditing tasks. So what we tried to do was we prompted these two different models, GPT 4.0 and Gemini Pro models, with this natural language prompt saying, I'll provide you with a photo of a streetscape from the United States, and please detect the following 10 objects in the image. So these are the 10 objects that we prompted in, which pretty much could be included, very likely to be included in an auditing task, such as vegetation, like trees, vehicles, bicycles, roads, sidewalks, benches, trash bins, streetlights, and traffic signals. And then having a little bit of more awareness of how these tools are now operating, we try to also give a more structurized, to output in a more structured format, such as saying, if the object is present, respond as 1. If it is not present, respond as 0. If the image itself is invalid, so that you cannot interpret anything out of it, output 9, so that we can automatically filter it afterwards during the post-processing steps. So these were this is a prompt, and we try to have Columbus, Ohio, which has a very clear urban and rural gradient in terms of their geography, as our case study. So we did it for 2,000 Google Street View images in Columbus, Ohio, and compare it with deep learning based image segmentation methods. And surprisingly, these LLMs showed over 90% agreement with the deep learning based image segmentation methods. Even, I mean, the average was 9.9 for ChatGPT and 9.7, which is very much similar between the two. But there were still some considerable variations in the agreement scores when you looked at individual built environment elements. As you can see from here, the tree, bicycle, and roads, which are very much obviously being able to be detected, nearly showed a perfect match with the deep learning technologies, almost approaching 100%. Whereas in specific elements, there was ChatGPT being better, in some cases Gemini being better, and in some cases both not reaching 100%, but still exceeding 70 or 80%, which is still considerably a good result. But we also observed that there is still a potential geographic disparity in the usability of such methods. So what we try to do was we try to do a global Moran's eye test. So this is a spatial clustering method to see if a high results cluster among themselves and low results cluster among themselves, which were pretty much true only for the case of using Gemini. So in case of ChatGPT, it had a relatively even distribution of the results, which means that even in the downtown, even in the rural, the outskirts of the city, the results were pretty much similar. However, when using Gemini, high results clustered mostly in the city center, whereas if you go out in periphery, the results were going lower than expected. Which means that it does underperform in specific regions of the city, particularly it will be where it's less urban, less populated, and if so, the people in there or for interpreting the doing the auditing task for images there pretty much will not be performing as well as possible. So we should be also aware of such limitations. But still, overall, we feel that these LLMs are actually more accessible to users and can actually democratize access to advanced tools that once only the experts could do for built environment auditing, such as using the deep learning technologies for that task. However, now this can democratize the such tasks for urban planning without any coding skills and without any high performance computing resources. And by doing so, it can also benefit these local governments or the city planners as it can be done in a very easy way, and just by prompting with natural language text. And then we try to suggest a potential need to shift the focus toward assuring data quality. So it's no more about the models, it's no more about the specific methods to do the task. It's about how can we guarantee that there is good quality, good amount of data, evenly distributed across the city, so that not only the city center it is benefiting from such technology, but also it is just an equitably benefiting the entire city as a whole. So probably this would be another task that the data collection at a regular scale to update the street images at a very high quality will be an important task for the city governments, and that will be that we believe that will be a very important assets in the future. So this is more of a practical exploration, how it can be used in a specific task that the city governments would do in the future. However, we try to also ask, even though it is powerful, even though it is promising, would it be actually used? So what will be the actual factors that people would consider if they were to accept these technologies? And this is actually a known notion as promise gap, which means that there's a gap between the perceived and realized benefits of technology. And here, according to the Global City Leaders Survey last year by Deloitte, they surveyed these global city leaders with this question: how are you feeling that these technologies are powerful enough or effective compared to how would you actually use it within the 3-year span? And on the rightmost column is the generative AI technology, and 58% of state leaders actually expected that it is powerful. You know, there's potential to use it. However, only 1% currently view it as very effective. So this connection implies that there is there implies the historical patterns in planning support systems when adopting a new technology. So it would be powerful, but would you actually use it? So this has been an ongoing debate when a new technology is coming in, and if the city governments are actually trying to adopt it for practice. So having this prompts gap also in the case of generative AI, we try to ask these questions: which capabilities of visual Gen AI are perceived as most useful for city design workflows, and how would these perceptions shape attitudes toward adoption? So what are the perceptual qualities that is important for the adoption? And then how would hands-on engagement with these tools shape planning community members, shape their perceptions and attitudes toward the adoption in a participatory manner. So what we did was we designed this workshop at MIT, which was a 3-week, a 3-time workshop, one per week, where we invited participants to freely join, regardless of their familiarity or experience with engaging with the generative AI technologies, especially DALL-E, which is a visual generative AI of OpenAI using GPT models. And we asked them to design a street based on like their interests. So try to design a street that is much safer, much livable, much beautiful, and so on and so forth. And then after all that, we try to do based on a technology acceptance model, we try to survey the perceived usefulness, the perceived ease of use, and their attitudes toward using such technology. And this was done by with the members of the academic planning community. The interesting thing was that the initial findings was that familiarity strongly increased post-intervention, which is very obvious because you after the intervention you get more familiar, and then also the perception metrics did increase for a strong if you have higher proficiency. So if you know generative AI or if you are aware of it, your perception metrics do increase in a positive tone. Uh, the more interesting part was when we had an interaction term between time and proficiency together. It was found that lower proficiency users did show stronger interest and engagement in city design after the intervention. So we were able to increase their engagement with these new tools if they were actually having a lower proficiency from the beginning. But who were already high proficiency participants saw the tool as more indispensable, which means that they knew already the tool that it has some effect, it has some impact, it can be a powerful tool, but after using it, that kind of reinforced that mindset and said, oh, maybe this can be actually really necessary. So it's the difference between whether who had low proficiency and high proficiency and what they value more in engaging with these technologies and how they try to adopt it. And overall, and after all that, we also try to look at the relationship between their perceived usefulness and their attitudes toward adoption. It was found that it was the cognitive and participatory dimensions that were more effective, whereas the operational perceived usefulness were actually not significant in pre-intervention stage, and even after the intervention, it was very low. So the conclusion here was that the cognitive and participatory dimensions did matter the most, while operational concerns are far less influential, which, for example, were the accuracy or realism. So it's not only the performance that, it's not actually the performance or how well the outputs look like, it's how the users would feel or more engaged to while using these tools. So, and then through having these engagement participatory workshops, we believe that hands-on engagement can also make it more easier for people to feel more familiar and feeling a positive attitude toward its adoption. And by finding these results, we feel that visual Gen AI tools do have strong potential for educational purposes as well. So it is trying to lower the barrier for first-time users because it is actually the low proficiency users who feel even a stronger interest and engagement after all these survey experiences. So these are two fun experiments that we did while trying to use how it can be adopted in either built environment auditing or city design workflows. But is it only promising? We do want to suggest some limitations or some important messages behind to use it in a good way. One reason is we find that there is a sign of stigmatization. We prompted Mid-Journey to say to draw an image of a residential apartment building in Brazil, and this was how it looked like. However, if we add favela, which means the informal settlements, it just suddenly degrades the quality of the built environments. Similarly, we try to ask DALL-E the street level scenes in Boston, the residential area of the white community, which looked like a very nice brownstone housing areas. However, we just change white to black, suddenly degrades the built environment with all the cracks, unmanaged, the bushes, the street poles, the wires, and so on and so forth. These The white and black is just merely a color. It doesn't necessarily imply any bias behind it. However, it is reinforcing the stigma behind what we might have as humans and is actually portraying and we all know that the outputs are also can also be refed into the training process. So it may have a power to reinforce such stigma that we as humans have in the real world. And there's also a geographic bias in the responses when we prompt it with environmental justice questions of each of the contiguous U.S. counties. This is how it looked like. So the blue ones were where it did output successful results for environmental justice issues of the corresponding county, and the red was where it did not respond properly. And it has a very clear division in the geography. So the coastal areas were performing much more well, much well, and it was found that counties that are more rural and poorer have a higher chance of not receiving local specific responses when using ChatGPT, particularly when prompting for environmental justice issues. So, for example, if the local government people try to use ChatGPT for their in practice in real life, asking for what may be the local issues here, they might not get the good results in specific areas. So there would be people who are benefiting with these tools. There would be areas who are not benefiting with these tools. So how should we address these issues? So these are some of the biases, some of the limitations of these tools that I would try to equally highlight and try to raise a question so that we can all collaboratively think about together to see, to discuss how we can use this in a better way for city planning tasks. So this is truly a black box. We don't know how it's operating fully. However, I was trying to show through this presentation what are the good sides, what are the promising sides. In the meantime, what are the limitations and biases that we should be very carefully looking into at the same time. So I do not want to put an answer for this for now, but I'd like to open up the discussion in the Q&A part and trying to have a more balanced talk about these tools when it comes to being adopted for city planning and design tasks. So thank you.
Thank you, Timo. And all right. So before we go to the question and answer, I'm going to talk very briefly about my research. Since we don't have that much time, I'm going to just dedicate a very small part to this. Let me share my screen. I hope that you all can see my screen right now. If you can see my screen, it would be great to just give me some signs, but I'm going to go through with this. Perfect. All right. So with the amount of information being continuously collected, it is very tempting to think that we now have the world at our fingertips and we can run any analysis we desire. But if we look closer, we see a large gap in the available data at the global scale. While every corner of every large US city is captured in Google street level images, the streets of capitals of many of the countries in the global south, where their names are not even labeled on the maps. Even within the data affluent nations such as the United States, we see a clear inequity in what data we have and whose interest it represents. Data availability drives where decisions are focused. For instance, while a third of the US population are non-drivers, federal transportation funds have historically been skewed towards automobile and overlooked active transportation. This pattern of systematic disinvestment, we can see it in the normal lives of people. For instance, these are some of the tweets and talks and experiences of day by day of people dealing with these type of infrastructure that we have. And the problem is not only limited to the surface or like inaccessibility, there is a lack of reliable data on where sidewalks, footpaths, and crosswalks are. Most navigation apps still rely on the road networks that assumes that there are sidewalks on both sides of the road. And as we all know, it's not a correct assumption, specifically in the United States. Having access to all services our cities have to offer is a human right. Is driving a choice, or is it a surrender to the current circumstances? Is it possible for an adult non-driver to rely on the current condition of the urban infrastructure to address their daily needs? To be able to answer these type of questions, we need to be able to do a comprehensive analysis of our pedestrian infrastructure. And any comprehensive analysis of pedestrian infrastructure needs a threefold understanding of where sidewalks are, how they are connected, and what their condition is. Well, we have sensors all around us collecting data on even like the types and species of the trees and the numbers of them. The data that we have from sidewalks is hardly enough to draw any informative picture. This lack of data leads to us not being able to assess the condition. And then we cannot address something that we know it is its extent, and we cannot know like, what the problem is. And to know that, we need data. So in my research, my goal and aim is to address this lack of data and to tackle it through providing open source and easy to use tools for people to use. And on city scale, I'm using aerial imagery, and on human scale, I'm using street level imagery. I'm going to only talk about the city scale, where I use aerial imagery, and I created this open source tool called Tile2Net, which is an end-to-end open source tool for creating pedestrian networks from auto-rectified aerial imagery. I use computer vision model to detect sidewalks, footpaths, and crosswalks from high resolution aerial imagery. And despite the complexity of the source code, we created a very user-friendly interface where the user can run the whole system for the areas that we support, only using just one line of code from command line. And when Tile2Net was published, it really received like lots of attention, and the attention was a testimony to how much this tool was needed, not that much how good the tool was. And the tool has been recently added to the ArcGIS Living Atlas and has been downloaded around like 18K times by now. And briefly, this is the pipeline of how Tile2Net works. It has like two different main parts: feature detection, where we have like this, we train this computer vision semantic segmentation model that can detect these features from the aerial imagery, and these features are in raster format. Then we take these raster predictions and we georeference them, creating maps that has like the geometry and also like the information of where they land on the surface of the earth. We have a polygon, and then from polygon we create the line representation. And here is the result. And as you can see, because this model was trained on the planimetric data, we can see that it could actually like overcome lots of the obstruction that we see from the shadow or vegetation. And also, this is the result of applying the model on the tiles from the Boston Common. And you see the aerial imagery. In the middle, there is this polygon data. And then on the right panel, we have like the line representation. And this is the city scale application of Tile2Net over Boston, Manhattan, and Washington, D.C. And the strength of the model here is that it can actually like tackle this on a larger scale with a lower cost. Perfect. All right. So now I want to invite everyone to first like our audience to send their question, and also for us to get together for and get ready for a like brief discussion. All right. So we will like the session will end in around like 11 minutes. So we have 11 minutes to do the discussion together. If we have any question from the audience, I'm happy to share it right now. I have a question for you. So we have a question, and I'm going to read it out right now. So the question read, I'm currently developing a method for generating building in project areas. However, not all generative methods have metrics that can be used to evaluate the generated buildings themselves, but only, for example, the quality of the generated image, not the building themselves. Do you have any case metric selecting for the evaluation performance of generative methods in relation to the generation of physical objects, such as buildings? The most obvious metric for me right now are FAR, building density, etc. Oh, all right. So I want to give the floor to Eric right now, and I think he can lead the discussion from this session on. Eric.
Thank you very much for this all the presentation. Very technical and with different topics that is useful for I can say all cities at all scales. So it's related to the data analysis and how to use AI in a prediction manner to deliver better services for cities. So this is very interesting. I would like to ask the panelists on the scale because we are here in the webinar of MeTTA, so looking for megacities, and how we can use this analysis at the scale, not at the scale of the neighborhood or the local scale, but how we can amplify the tools you are developing regarding at the scale of the megacities. What are the main concern or the main tools that we can imagine using LLM and the AI to modelize, to prepare policies or territorial strategies at the scale of megacities. I think this, because when we speak about megacity or something which is more complex than a small city, and so probably there is some other methods to develop really specific for this very complex bodies. So perhaps the panelists can elaborate on that, please.
Yes, I think I can start answering to that question. Thank you for raising a very important question, especially when it comes to the megacity context, how we can scale up in the megacity scale. Related to the presentation that I did for my projects, I mentioned about the importance of now the data quality. I think the megacity governments can focus on how to ensure that there is a very good quality data set at a large scale, and that's where I think the big city governments can contribute to in securing a very good asset for urban analysis at a massive scale. Now, the models, especially because I presented about the LLMs, models can be openly accessible or through subscriptions. You could be able to fine tune it yourself for specific purposes, but still, if the open models are still very powerful in terms of the performances, it's now how, like, which city or which government is having a very good quality data set at a large scale. I think that's where big city governments can contribute to more. I know that Amsterdam, our lab has a very good connection with the Amsterdam Institute, AMS. And we learned a lot from the Amsterdam city that the city government is putting a lot of efforts to have their own like street view imagery data set at a citywide scale, a LiDAR point cloud data set that the city government people or the researchers that are in-house in the city governments themselves collect and gather and pre-process it for that in a quality that is readily accessible for research. Why this is important is because also in the street view imagery realm, people are trying to diverge from relying on like private sector such as Google Maps, because then if so, we always have to ask for like API requests, and sometimes they are even deprecating the APIs that in one day we might be having a limited access to the data, and if so, the research capabilities would decrease at some point. So they're trying to gather their own assets that they have their own rights of usage. So I think that's where the governments can also contribute to a lot. Another is that very briefly, another is that I mentioned about the educational purposes, especially for the low proficiency users. I believe that if the government can also offer some educational programs so that first-hand users can have their very first experiences of these new tools or of these AI technologies, it will be very helpful for them to get more engaged and be more willing to adopt the technologies of the future.
Thank you. Other panelists?
Yeah, maybe from my side, Eric, I'm not a technical specialist, maybe than like Mr. Zhang, but in our case, working with generative AI, maybe we try to make a segmentation of the data sets, no? Because as you probably know, the large language model can work around 1 million tokens of context window, no? So maybe it's preferred to make a segmentation of these data sets. But for machine learning model developments, I think that in some projects we use clustering techniques. In machine learning projects, it's more easy to make a more big context, but you will need more time of process of your CPUs, of your machines, but you can use clustering techniques for this kind of AI or traditional AI solutions.
Yeah. Interesting. Junior?
Yeah, I would like to talk about the usefulness of this kind of approach to the megacity the 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 deal with the megacity problems. That is not just the extended approach using the more large scale data, but we need to find some the fill the gap between the administrative planning and the this kind of mobility based planning. That means we can we can find some the discrepancy or the special uh, the inequality place, and by detecting those kind of unequal place that the service is not evenly provided, it will be very helpful by this kind of data-driven, mobility-based approach we can adopt, then it can be helpful to many the megacities.
Thank you, Miriam.
So yeah, thank you. I think we only have 2 minutes right now. And yeah, so like my very brief answer is I think like a big chunk of it depends on the quality of the data that we collect. Because right now, I think one of the main problems of many of these, let's say LLMs and the large language models that we have is garbage in, garbage out. And we don't have any data quality control over what is going in these models and what type of biases is going to be, instilled in these type of models. And then what are the type of biases that they propagate again after being trained on all of those data. So maybe having some filtration and some quality control will help us get way better results than focusing mostly on the, like making them like 1% better than what they are right now. So this is, I think, where specifically for the fields where we are working with humans and with the very sensitive data, it is where our focus should be.
Thank you. Perhaps you can go to the question from the audience.
Yeah, actually, I wanted to ask the audience that I read their question to actually email me, because this is a question that we can discuss and this is something that I work on. So I can help them maybe like with the question of how to evaluate, because this is a field that I'm actively working on, developing new evaluation metrics for these models, because we are not right now, we don't have those evaluation metrics available for many of these type of analysis. So yeah, you can email me and maybe I can help you with that. And I think, yeah, we are at the hour. So just as we close, I wanted to underline that, aside from like all these having the machine learning and AI, which is fantastic and it is helping us a lot to scale up our analysis, one thing that we should not forget is we need the human experience and expertise in the loop of training and in the loop of development, and also having this connection between the research institute and different interdisciplinary researchers. And I think this is precisely the role that the Megacity Think Tank Alliances want to play to bring us like and all of these types of like a research centers together. And I hope that we see more of this happening across different, interdisciplinary research, because urban analytics in nature is a complex system that needs interdisciplinary approach in order to be, like reaching a conclusion and a good outcome with all of these type of decisions that we want to make, whether using AI or whether using any other technique.
Yeah. Is there any other questions? So you want to we continue, or because there is
No, I think there is no
Okay.
other question. I just checked.
Okay.
And with that, I wanted to just close the meeting today. Thank you everyone for joining us, to our great panelists, and to Dr. Choi and Eric and everyone. And I'm very happy to be here and hope to again collaborate soon.
Very
Have
good.
a
Thank
great
you.
morning and
Thank you
evening.
very much.
Thank you.
Bye
Bye.
bye.
Thank you. Bye.